In this video, we're going to look at the Lewis structures associated with some of the polyatomics. We're going to deal with the polyatomics first on their own, and then we're going to deal with them as they would likely to be as a part of an ionic compound. Also, while we're here, we're going to look at some of the special types of bonds, and maybe they'll be illustrated through polyatomics or not. So let's just start with the polyatomic SO4 2 minus. Okay. Here, actually, you know what? We're going to skip that one just for right now. Let's do CO3 2 minus. Here, the way we're going to handle this is we basically recognize that this extra charge here is going to be a reflection of having 2 more electrons than we expected to have. And so we'll find our total number of electrons normally, and then we'll add 2 for the 2 minus charge. So carbon would typically contribute 4 valence electrons. Each oxygen would typically contribute 6 electrons, and we have 3 of them for a total of 18. So 4 plus 18 would normally have been 22, plus we get 2 extra electrons from the minus 2 charge. And so when we're making this Lewis structure, we have 24 electrons to work with. Here we can see we have 1 carbon and 3 oxygens. And so we put the carbon in the middle, and we put the oxygens around the outside, just like that. Now the way we're going to handle this is we're going to put 1 bond to each oxygen first, and then since we don't have any hydrogens here, we're going to octet each atom, or we're going to fill each atom up until they have 8 electrons. So if I look at this oxygen to start, I have 2 in the bond, there's 2 more, there's 2 more, there's 2 more, for a total of 2, 4, 6, 8. If I look at this oxygen, 2 here, 2, 2, 2, there's my 8, and similarly with this oxygen. Now, I think a lot of times when students octet atoms, they forget the central atom. Here he has 2, 4, 6 associated with the bonding. He needs 2 more electrons to make an octet around himself. So let's count electrons and let's see if we have too many or too few. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I'm currently sitting at 26. I'm supposed to have 24, so that means I have too many. The way that I handle that is I take off 2 electrons here, 2 electrons here. Which oxygen I choose to make the double bond with was an arbitrary choice. We're going to come back to that later. But right now I just randomly chose this one right here. And by doing that, if we see, I removed 2 electrons that were here and 2 electrons that were here, and replaced them with just 2 electrons shared in a way that they octet both atoms, but at the same time lower the overall number of electrons by 4 down to 2 by 2. Counting again, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now I've reduced it to 24, which is how many I need based on the overall number of electrons I had to work with in the first place. Because this atom has a charge, I put big square brackets around it, and I say it's 2 minus. So that's the Lewis structure for carbonate. Now, most likely, if we have something like carbonate or sulfite or any of these kinds of things, they're going to be part excuse me, of an ionic structure. So I gave this atom 2 extra electrons here because of its minus 2 charge, and I don't know if that made anybody think, but where did those 2 electrons come from? Well, chances are if this thing existed, it would really exist as a ionic substance here. So if I want to do the Lewis structure for this overall ionic substance, basically what I do is I treat it as 2 individual ions. I do the covalent structure for the sulfite on its own. I do a big Lewis structure there, and then I have the sodium. It's simple because it's just the sodium having lost its electrons, and then I can put it together into a bigger Lewis structure. Let's use this as an opportunity, though, to do an example. If I really think about this, this would be sodium plus, and I have two of them, and then I would have my big sulfite ion, and that's going to have a charge of 2 minus. Sulfur offers 6 electrons in its valence. Oxygen there are 3 of them with 6 electrons each. So that's 18, which would give me a normal total number of electrons of 24, plus 2 electrons from the 2 minus charge here. And now that we see him paired with sodium, we kind of have a better idea of where those 2 electrons came from. Those are the 2 that were stolen from sodium when the ionic bond was formed. But in the meantime, what's important is that we have 26 electrons in our valence structure. Setting sulfur as the center and octetting everybody. Again, a quick reminder that when you're octetting everybody, don't forget to octet your central atom as well. So let's count here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I think I'm okay, but I was having a little trouble counting there, so I'm going to try it one more time. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I'm good here, and I only have one sulfite in the overall atom, right? Like if I was to consider it to be a 1, so I don't have to put the 1 down here, but you can imagine that it's there. And that's how I would do the Lewis structure for this ionic salt that results between a metal and a polyatomic. Okay. Now we're going to look at a couple interesting types of bonds that exist in, they exist in the polyatomics, but they don't necessarily have to exist in the polyatomics. The first one we're going to talk about is a coordinate covalent bond. And this is an odd situation where one atom contributes both of the electrons that's involved in one of the covalent bonds. My example molecule here will be carbon monoxide, CO. In this situation, carbon offers 4 electrons, oxygen offers 6, and so I have a total of 10 electrons to work with. If I go ahead and octet both guys, put one bond in between them so they're at least bonded, and then I count 2, 4, 6, 8, 10, 12, 14. I can see in my structure I currently have 14 electrons and I only have 10 to work with. That means I have to make a double bond. And now if I count again, 2, 4, 6, 8, 10, 12, still too many. So again, if you'll recall from Friday's lesson, I said don't make a triple bond unless you absolutely have to. But if you have no choice, you have nowhere else to go with it, make a triple bond. So there we go. We have 2, 4, 6, 8, 10 electrons. We're out of 14. We're down to the 10 that we needed based on our predicted number. What's interesting about this, though, remember, is that this carbon offered 4 and this oxygen offered 6. If we imagine that 2 of these carbons are sitting here, and then we say carbon offers 1 of the 2 electrons in this bond and 1 of the 2 electrons in this bond, then what I get up to is 1, 2, 3, 4. There's my 4 electrons. Carbon doesn't have any electrons left over to contribute anything to this last bond. What that means is that both of the electrons that are involved in this final bond and the triple bond must have come from oxygen. Both electrons. That's pretty rare. And when it does happen, it's a pretty unstable situation. Again, if I count the oxygen electrons, 1, 2, 3, 4, 5, 6, and you can see that he's contributed both of the bonds there. So that's what a coordinate covalent bond is. It's when one atom contributes both electrons in that covalent bond. Okay, sorry, just had to pause there for a second, but we're back going. The last type of situation, or the last type of bond that I want to discuss, just with its own special little name, is a resonance bond. And this occurs when the location of a double bond that we chose was arbitrary. I don't need to do another example here. We've seen this already when we were looking at carbonate. If you recall, I got to this part of the solution for carbonate. Can't remember how many electrons I had. I think it was 26, if I remember. Yeah, I had 26 electrons, and I knew I had to go down to 24 because of the totals associated with carbonate. And what that meant was that I had to make a double bond. Well, I can make a bunch of double bonds equally reasonably here. When I did it in the first place, I made the double bond in this location. But I can make it here just the same. So when I make that double bond, the structure could turn into this, this, or this. What really happens is that all three of these will occur to some extent within the molecule or within the substance. And what that means then is that this double bond isn't a specific local double bond, but it's one that's in an arbitrary location and in a sense is shared between all three of those oxygen atoms. It gets a special name, resonance bond, because it does affect the properties of the material. This double bond will be a little bit more stable than a double bond that would normally be seen in this type of material. And, well, that's basically it.